Welcome to lecture 40. The title of this lecture is Nagaoka Ferromagnetism. In these last two lectures of the course, we're going to delve a bit into mathematical physics. I'm going to prove some rigorous results about properties of the Hubbard model. And this first one is a very famous result from the mid-1960s that showed that in certain cases the Hubbard model would have a ferromagnetic ground state. So we're going to take our Hubbard Hamiltonian and we're going to write it in a more general form than we had done it before. We're not going to necessarily assume we have hopping just between nearest neighbors. So we're going to use a hopping matrix Tij, but we're going to still sum over all spins sigma, and that's been given to you explicitly here with the C dagger I up, Cj up, plus C dagger I down, Cj down. The matrix Tij is a Hermitian matrix, and in this case it's going to actually be a real symmetric matrix, and we have to recognize that I need both the Tij and the Tji terms, which will have exactly the same value. Unlike in the previous cases where we were summing over nearest neighbor pairs, here we are looking at each of the contributions of the pair, and the hopping from 1 to 2 is incorporated in one term, and the hopping from 2 to 1 is incorporated in another term, both with the indices 1, 2, and with 2, 1 in the way that this is written. You should just be sure you feel comfortable and understand how that works. Then the second term is the standard Hubbard interaction term, and we haven't done anything with that. Now there's a condition on the hopping matrix for this Nagaoka ferromagnetism to hold, and that condition is that the Tij's are all non-negative, which means they're larger or equal to 0, but otherwise they can be arbitrary. And of course, because we have to have a symmetric or Hermitian matrix and these Tij's are going to be taken to be real, we must have Tij is equal to Tji. The lattice is going to have capital N sites, and we're going to consider the limit as u goes to infinity, and the case where the number of electrons is exactly 1 minus a half-filled band. So the number of electrons is capital N minus 1. Now you should recall that when u is equal to infinity, there is no double occupancy. So the following set of states can serve as a basis. We're going to call the state I comma sigma, and it's going to have a phase factor in front, which is minus 1 raised to the ith power. It'll have a C dagger 1 sigma 1. So sigma you can think of as a multi-index. It's an n minus 1 fold index, or even I think we'll be using it as an n-fold index. But if you notice here in the state that we've created with the C dagger 1 sigma 1, C dagger 2 sigma 2, C dagger 3 sigma 3, notice that the C dagger I sigma I term, that term is not there. So we call that a hole. That's the absence of an electron. And so what this state is it's a state that has n minus 1 electrons, and each of those electrons has a spin configuration given by the sigma 1, sigma 2, sigma 3, etc. And there's a hole at site I. And so that's why we use this symbol I comma sigma to denote this state. And we need to recognize that that sigma is this multi-index sigma 1, sigma 2, all the way out to sigma n. Of course, sigma I will equal 0 in that notation. And that's because there's no electron at that site, so there's no spin associated with that site. So we're now going to actually think of these states as sites on a metal lattice that is constructed out of these many-body states. You see there's a natural sort of order to these states. They're denoted by an I and a sigma. And we're going to say two of these many-body states, I sigma and J tau, are connected if the matrix element of the hopping matrix between these two states is not equal to 0. Now from a physical principle, what this says is I've hopped such that the hole at site I has moved to site J. Let that sink in for a moment. The hole at site I has been moved to site J. How do I do that? Well, I have to hop from one of the neighbors of site I to fill that site J, to fill the hole at site I. And so what that means is J must be a nearest neighbor to I, or a neighbor to I that is connected by a non-zero Tij, and then I'm hopping a electron from site J to site I to fill the hole at site I and create a hole at site J. And then, of course, the spins of all of the other terms must be exactly the same, otherwise it won't be the same state. And so we're going to use this notation with a double arrow to say that Ij is connected with, I sigma is connected with J tau. And the condition, as we just sort of worked out in my discussion there, is that the sigma alpha is equal to the tau alpha, except for alpha equals I and J. And we'll have sigma J is equal to tau I. Of course, sigma I equals tau J equals 0 because there's a hole there. And then when we calculate this matrix element, take that C dagger I up, Cj up, plus C dagger I down, Cj down operator and act it on the I sigma state. And then we have to put it back into the J tau form. We're going to need to move the C dagger J sigma J operator from the jth location to the ith location. And in doing so, it's going to go through a set of J minus I plus 1 different terms in the ordering that we have due to interchanging the creation operator. Now, using the fact that the state is defined with a -1 to the I or a -1 to the J, what you see as the net effect is that when that hopping term or the kinetic energy operator acts on an Ij, it produces minus the J tau. And so when I take the overlap with a J tau, we're going to get minus Tij. That is really the critical observation in order to carry out this proof. Please be sure you understand exactly where that minus sign comes from. Again, let me say in words what is happening. We have to move our C dagger operator from the J position to the I position to fill the hole. In doing so, I have to move over I minus J minus 1 different C dagger operators that are in the way. Each one of those will give me a minus sign, and then due to the fact that we put in a phase of -1 to the I for the I sigma term and -1 to the J for the J tau state, the net effect is that we're going to get a sign change of that state from what the J tau state is. And so when we calculate this matrix element, we get a minus Tij. Now, the second condition we have to look at is we're going to say that a lattice satisfies what we call a connectivity condition if for every state I sigma with a fixed value of Sz, so that's just the sum of all of the sigma i's, there is a finite chain starting from I sigma 1 through J sigma 2 to K sigma 3 all the way to L sigma n that connects each state I sigma 1 to L sigma n. Then we would say that the states I sigma 1 and L sigma n are connected. Another way of saying this is if there is any way to hop and fill the hole at site I with the hole at site J while converting the spin indices from the spin indices sigma 1 to the spin indices sigma n via just doing hopping, then we say that those two states are connected. Now, it turns out that every state with the same value of Sz is connected when the lattice satisfies this connectivity condition. And the primitive condition you need in order for that to be true is these two conditions. So for every site I, we either have Tij, Tjk, Tki does not equal 0. That means I have a triangle as illustrated here on the left. Or we have Tij, Tjk, Tkl, Tli is not equal to 0, which means we have a lattice that schematically has a square in it as indicated here with the Ijkl. And there is at least one site other than the site I that is connected to all other sites via a path of hopping matrix elements that does not pass through the site I. So if that condition is true, in other words, there's two ways to get to site I, then this connectivity condition will be true. We're not going to prove that the connectivity condition is true if these primitive conditions hold, but we will simply state what lattices this holds for, and that includes the square lattice, the triangular lattice, the simple cubic lattice, the body-centered cubic lattice, the face-centered cubic lattice, and so forth. They all satisfy this connectivity condition. The only lattice that does not, that is one that you commonly will encounter, is a one-dimensional lattice with nearest neighbor hopping, and that's because it does not have another site I that is connected to all other sites via a path of t's that does not pass through site I, because on the one-dimensional lattice there is only one way to pass through site I if I have nearest neighbor hopping. Okay, so let's get to the way that we're going to do the proof. It's a variational proof, so we're going to just construct some state that I'm going to call psi, which has a set of numbers, psi I sigma, summed over I and sigma. So it's a linear combination or a superposition, arbitrary in this case, over all of those many-body states I sigma. And we're going to just insist that it's a unit norm state, which means that if I take the norm of psi with itself, because these states are orthogonal to each other, it's just the sum over I and sigma of this psi I sigma modulus squared, and we're going to require that total sum to equal 1. Then what we're going to do is we're going to choose a state phi, which has a sum over I of phi I, and then the spin configuration is all spins up. Now the spin configuration with all spins up, that is obviously a ferromagnetic state because everything is aligned in the same direction. And so that state must have this total spin is equal to the maximal total spin, which is n minus 1 divided by 2, because I have n minus 1 electrons, and each electron will have a spin 1/2. What we're going to do is we're going to choose the numbers phi I to be the sum over all spin configurations, keeping the whole at site I, the modulus squared of those psi I sigmas. And we're going to take the square root of that. Now, because that is a sum of real numbers and I take the square root of it, and they're all positive numbers, that number is obviously real. So the phi i's are all real, and if I look at the modulus squared, or take the norm of the state phi with itself, since that's the sum of the phi I squareds, that is just going to equal 1 as well, because it's the same as the sum over I sigma of modulus psi I sigma quantity squared. Okay, be sure you understand that. That's the reason why we took this particular choice. Now, the second condition that we get is that when I look at the kinetic energy matrix element between a psi, remember that is going to give me a minus Tij, that's the matrix element, and it's connected to a j tau, so I'm going to get a psi j tau star, psi I sigma, and I'm going to have to sum over all j taus that are connected to I sigma via one hop of the hopping matrix. I have to sum over all of those. The claim is that is larger or equal to the sum over ij of minus Tij phi j star phi I. Note that that term on the right-hand side is just the variational energy, kinetic energy of the state in the state phi. Now the inequality comes from something called the Schwarz inequality. We have covered this before in the class. That looks at an inner product between two vectors A and B, which can be written as a sum over alpha A alpha star B alpha, and that's less than or equal to the norm, the product of the norms of each of the vectors. The square root of the sum over alpha modulus A alpha squared multiplied by the square root of the sum over beta modulus B beta squared. Schematically, I write that as A dot B is less than or equal to the norm of A times the norm of B. Now the proof of this is something that we have proved before. I'll just sketch it for you once again. We have, if you look at the state A minus lambda B and take its norm, that must be greater than or equal to 0. If you work it out, you get an A squared minus 2 lambda A dot B plus lambda squared B squared. That means A dot B is less than or equal to 1 over 2 lambda mod A squared plus lambda over 2 mod B squared. And we simply choose lambda equals mod A over B, and you find A dot B is less than or equal to a half A times B plus a half A times B, which is just equal to A times B. And so that's the way that you prove this Schwarz inequality. If we choose A sigma equals psi j tau and B tau equals psi I sigma, you see then that the sum over sigma of modulus A sigma squared, that is equal to phi j. and the sum over sigma of b sigma squared, that is equal to phi I. And so that's how that result holds. And again, let me show you what that inequality is. We have essentially proven this inequality in the middle of the page. And because that is equal to the variational energy, if psi is a ground state, then the variational expectation value of the kinetic energy is equal to the ground state energy, because remember, there's no double occupancy in that state, so the U term, its expectation value is 0. But then phi has the same energy, because the expectation value of phi is less than or equal to the expectation value for the psi, which means the phi state must also be a ground state. So if psi is a ground state, then phi is also a ground state. Let me make sure you understand what this means. What it says is, if you tell me that you have found a ground state that has some spin that is not the maximal spin, then from that ground state that you have found, I can construct a new ground state that has maximal spin. So it says amongst all of the different ground states that you might have in your system, there is a ferromagnetic ground state as well. It actually turns out that this ground state is unique, and the ground state is truly ferromagnetic, and that's something that requires a little bit more work to prove. Instead, what I'm going to do is I'm going to focus on proving this with something called the Perron-Frobenius theorem. This is going to be a different way of proving the same result. And it's just a kind of a neat way of looking at this problem, and it's a fairly simple way of doing a very rigorous result, and it's a fact that you should really know. So at the moment, I'm not going to be thinking about the Hubbard model or Hubbard matrices or anything like that. We're going to just focus on general matrices, and we're going to consider a matrix M whose matrix elements are all larger or equal to 0 for I not equal to j. The diagonals can be any number, but the off-diagonal elements are all larger than or equal to 0. Then if Mij is connected, which means that any two pairs I and j, you can find a path of non-zero Mik. So you go Mi1, I2, Mi2, I3, Mi3, I4, etc., where I1 is equal to I and In is equal to j, and those guys are all non-zero matrix elements that connect the two sides. Then we say Mij is connected. Then what we say is the eigenstate of M with the maximal eigenvalue is unique, and it has all basis vectors with strictly positive coefficients. So that's a really powerful statement. It says that there's no degeneracy in the eigenvalues. The eigenvalue is unique, and you also learn that the coefficients of the eigenvalue all have the same sign, which is a pretty powerful statement. It turns out that the proof of this is actually quite easy to do. So the first thing we're going to do is we're going to let M be the smallest diagonal element, where a large negative number is, in this case, considered a very small number. And we're simply going to look at M prime, where we add the absolute value of M, Mij plus the absolute value of M, multiplied by delta Ij. That is a matrix that has M prime Ij greater than or equal to 0 for all I and j. And then the eigenvalue E prime is just equal to E plus the absolute value of M, because I simply added absolute value of M times the identity, and that just shifts the eigenvalues by absolute value of M. All right, so we're going to now suppose that psi I is an eigenvector of M prime, and some psi I are less than 0, and E prime is the largest eigenvalue. Then the eigenvalue equation simply tells me sum over j, Mij prime psi j is equal to E prime psi I, and we're going to now consider the state phi I, which is just the absolute value of psi I. We're now going to look at the block on the left. If we look at the absolute value of the sum over j of M prime Ij psi j, that is equal to the absolute value of E prime times psi I. E prime must be bigger than 0, and so that's equal to E prime times the absolute value of psi I. But the absolute value of the sum is less than or equal to the sum of the absolute value. Because all of the Mij primes are bigger than or equal to 0 and are real, I can just put that absolute value sign on the side j, and that tells me that the sum over j of M prime Ij phi j is greater than or equal to E prime phi I. Now, because all m prime ij are greater than or equal to 0 and phi j is greater than or equal to 0, all of the terms on the left-hand side are larger than or equal to 0. But that is not necessarily true for all of the terms for the sum over j m prime ij psi j, because some of the psi j's could be less than 0. That means if I look at this expectation value, sum over ij phi I m prime ij phi j, that must be larger or equal to e prime times the sum over I of phi I squared. All I've done is I've taken this inequality that we worked out, multiplied it by phi I, which is a positive number, and summed that over all I. The inequality still holds. That means phi I would have a larger eigenvalue than e prime. But that can't be true because our condition was that e prime was the largest eigenvector. So that means the phi I must be larger than or equal to 0 for the largest eigenvalue. So that's the first part of the proof. Furthermore, if the m prime ij is connected, then phi I must be greater than 0 for all I, so we can't have any zeros for the phi I. So to see that, consider the sum over j of m prime ij phi j equals e prime phi I. Remember, this is just the eigenvalue equation. And suppose we have a phi k that is equal to 0. Since k is connected to some k prime by a non-zero m prime kk prime, there will be some set of positive numbers because all of the terms on the left-hand side are positive, plus some m prime kk prime phi k prime, and that must equal e prime times phi k. Since e prime is not equal to 0, and everything on the left-hand side is positive, that tells you that the phi k cannot be equal to 0. So that's how we learn that the ground state is unique in the case where it is connected. Now, to prove the Nagaoka theorem, we simply apply this to a matrix given by minus h. You can show that such a matrix, when it's written in that many-body basis that we worked on, since all of the matrix elements are given by minus tij, that matrix is just given by tij, and we said that the tij, the hopping terms, are all larger than or equal to 0, and so that's enough to establish the proof. All right, it's time to summarize. For u equals 0 and m equals n minus 1 and tij all non-negative, the ground state includes a state with s equals n minus 1 over 2. If the lattice is connected, the ground state is unique, so the ground state is spin s equals n minus 1 over 2. For a bipartite lattice, this result holds for both signs of t, since we can change the sign of t with a unitary transformation. We find that this ferromagnetism holds also for u finite, but the critical u can be very large. As I reduce the u, eventually the system goes to a non-magnetic ground state. So there's actually a phase transition in the ground state as a function of u. Now, if m is equal to n minus 2, there's an overwhelming amount of numerical evidence that shows that the ground state is a spin singlet, but this has not been proven in general. And an important question that people would like to know is, does ferromagnetism survive for a finite density of electrons away from half-filling? In this case, we just pulled one electron out of half-filling. That's not the same as pulling a finite density of electrons away from half-filling. In the one-dimensional case, it turns out that this never holds for finite u. And for d, the spatial dimension going to infinity, it's believed that you have an unsaturated ferromagnetism. So that's also not exactly the Nagaoka state. But there are a number of special lattices that people have worked on where they can show that this Nagaoka ferromagnetism does survive. And I want to just end this lecture by saying this is not just academic pie-in-the-sky stuff, oh, hey, here's something neat we can prove about the Hubbard model, although that is also true here. Just this year, in March of 2020, there was a publication in Nature where people actually set up this Nagaoka experiment using quantum dots. They had a 4-site lattice that they put 3 electrons in, and they could show when they could adjust the hopping so that all of the hopping matrix elements were larger or equal to 0, they could show that in that case, when the U was made very, very large, the system became ferromagnetic. And so this has now been experimentally verified that this is something that actually holds. The unfortunate thing is this is not the source of ferromagnetism in things like iron or nickel or any of the rare earth magnets or any of those kinds of magnets that you are familiar with that appear in your headphones or you use to stick notes on your refrigerator and so forth. None of those magnets are magnetic for this particular reason, but we now have actually experimentally verified that you can find this ferromagnetism in a case where this has been set up to satisfy this Hubbard model experimentally using a quantum dot quantum simulator. Okay, that is all for lecture 40. We have one final lecture left, and we'll do another mathematical physics looking at antiferromagnetism as opposed to ferromagnetism.